All right, welcome to Hamiltonian mechanics. We're not going to actually be talking about Hamiltonian mechanics. We're going to be talking about a lot of partial differential equations, but it's under the framework of Hamiltonian mechanics, hence I'm allowed to call it that. Before we get started, let's review what you may already know about Hamiltonian mechanics. So this whole approach centers around this nice function called the Hamiltonian. What is the Hamiltonian, you may be asking? Well, it is the total energy oftentimes. Well, in physics, it is basically all the time the total energy of a system. The total energy can be broken down into the kinetic energy and the potential energy. We often write kinetic energy as 1/2 mv squared. However, in more advanced physics classes, we tend to set m to 1 because it's just another variable and doesn't affect the dynamics that much. Another thing that has a formula in physics is momentum, and momentum is equal to mv, or simply v. Now, this means that we can oftentimes rewrite the kinetic energy as p²/2. And you'll be seeing this expression a lot. Now, the neat thing about this expression for kinetic energy is that it does not depend on a coordinate. It only depends on the momentum. And all of Hamiltonian mechanics centers around variable pairs, right? So we have momentum and its conjugate pair, the coordinate q, because q kind of sounds like coordinate. It's the same thing, right? And then the potential energy, it oftentimes depends on q itself, right? And q can just be anything like, I don't know, space or some angle, right? Now, P is a little bit harder to describe like this because it varies from system to system. It basically tells us what the system is like. But some examples are -1/2 kx² or kp, or kq² if you would like, right? This is the elastic potential. MGH or MGQ under this Hamiltonian notation. And yeah, these are basically the only two you're going to be seeing. Good luck. The neat thing about this whole approach is that these two little variables, they're related to each other in a very cool way that allows us to do a lot of things, right? So P is equal to negative partial H partial Q and Q dot, right? So this is the time derivative, the total time derivative. Dot indicates total time derivative. H partial P. And this is the backbone of all of Hamiltonian mechanics. First thing you're going to be learning in any Hamiltonian mechanics course. Now, this holds true for any Hamiltonian system, and it can also be a condition to determine if a system is Hamiltonian. However, this can be rewritten using something called a Poisson bracket, and Poisson means fish in French. So a Poisson bracket of two functions f and g is equal to partial f partial u partial g partial p minus partial F partial P partial G partial Q. This is a Poisson bracket, or at least the canonical definition of it. Now, this definition for the Poisson bracket has a few interesting properties. First of all, the two equations that we just got familiar with, or maybe you got familiar with them before. I hope you did. This is one cool thing about Poisson brackets is they allow us to do this, and this right here holds true even more generally. I may have flipped too much. The Poisson bracket thing holds true even more generally than this. So if we ever end up lost in the wild, lost in the desert, and we can't use this Poisson bracket, we have to use some other Poisson bracket, this will not hold true. But this will, right? So this is just a more general approach to writing Hamilton's equations. Now, a few other interesting properties that Poisson brackets can have, or that they do have if a system is Hamiltonian, is assuming that there is more than one conjugate pair, and conjugate pairs P and Q. The Poisson bracket between any two P's is 0. The Poisson bracket between any two Q's that are not the same is 0, provided I is not equal to J, right? This is important. And I think we can drop this condition. I think we can drop that condition actually. Yeah, this will always hold true, or this has to hold true if the system is going to be Hamiltonian. And gosh. The Poisson bracket between any pi and any pj is equal to Kronecker delta I of j. Kronecker delta basically means it's only going to be one of these two things are equal. Now, these three conditions together, right? These three conditions together, they're called involution, right? So if all these three conditions are met, then these conjugate pairs are considered to be in involution, right? Now, what these two conditions say is that every P and every Q is independent from each other, right? They don't influence each other's motion, and this is important in stuff like later action angle variable theory. I'm not sure if I showed this in my action angle variable theory video, but this is important for that. And this ensures that no P is conjugate to more than one Q, no Q is conjugate to more than one P, and also conjugate pairs are actually conjugate, right? So this is a pretty loaded condition. I remember I have a blank slide over there, don't I? I do. Okay, amazing. Now, let's try something. Let's try to get a Hamiltonian from an equation of motion, right? So usually how we go is we have a Hamiltonian and we get an equation of motion out of it. What I want to do is I want to start with an equation of motion, and I want to get a Hamiltonian out of it. Now, let's call Let's call this variable, let's call this variable theta. And let's set it equal to negative omega squared theta, negative a omega cubed. And I'm not calling it Q just yet because what we do when we want to convert a differential equation to a Hamiltonian is we must choose, yes, that's right, choose our Q's and our P's appropriately. Now, if you haven't been paying attention, you may think, hey, this is a total time derivative. And what else is a total time derivative? Our equations of motion, our Hamilton's equations, are our total time derivatives, right? But this isn't a first order total time derivative, right? It has two dots instead of one dot. So what do we do with that? Well, one way that we could go about this is we could simply choose p dot is equal to theta double dot. We're completely free to do that as long as we then follow a procedure to arrive at the Hamiltonian that is actually gonna be Hamiltonian. But if we choose p dot to be q double dot, then what do we choose q to be, or theta double dot? Then what do we choose q to be? Well, we could always choose q dot to be, no, we could always choose q to be theta, which means that q dot is gonna be equal to theta dot. And what else is theta dot equal to? Right, from this equation right here. This isn't something that you should be allowed to do, right? But I'm gonna do it anyways. Cancel one of the dots, and we're left with p is equal to theta dot. And this is allowed because despite the involution conditions, despite the conditions that p and q should be independent from each other, or no, every q and every p should be independent from each other, and also every q should actually be conjugate to its p. This is allowed, right? This does not break involution whatsoever, right? So now we just use this and we derive a Hamiltonian. Now, how do we derive a Hamiltonian? Well, we remember from our previous slide that these are the equations of motion. And the nice thing about partial derivatives is that you can integrate them, and you don't have to worry about any other equation that may also have the same function. You can just sum them later and don't worry about it. So this means that p dot is equal to negative partial h partial q. How do we get q out here? Well, we can move this negative sign over to here and then take the integral. That's exactly what we're going to do. So this is p dot, right? Let's firstly move the negative sign, right? And then let's integrate it. So how do I denote this? Let's denote it hp for the p component of h, I guess. Or no, hq for the q component. Yeah, because I'm going to be integrating with respect to, yeah. Omega squared theta. Actually, I don't have to write theta anymore. I can write q because I've already chosen it. Plus alpha theta. I said I don't have to write it anymore. And this is fairly easy integral to take. I'm going to take it in my head because I can do that. 2 omega squared q squared. I'm running out of word space. 1 over 4 alpha q cubed. Oh, q q to the fourth, q to the fourth. This is one part of our h, and the p part of our h, the one that's going to depend on p, comes from this equality right here, this equation right here. So what do we do here? We can take, there's no negative sign out front, so we don't have to worry about that. Right? There's no negative sign out front here, so we don't have to worry about that. So we can take the integral with respect to p directly. And what are we taking? What is the integrand here? Well, the integrand is just p. Well, and what is this? Can anybody tell me what this is? I'm staring down at an empty boardroom here. I don't have a lot to work with. Squared. Or, alternatively, and doesn't this look a little bit familiar? Doesn't this look a little bit familiar to you? Doesn't this look a little bit familiar? Doesn't this look just a little bit like kinetic energy? And doesn't this look just a little bit like a potential that we may be familiar with? That the simple harmonic potential? Yeah, it does. And this is just some other potential. So this together is still potential energy. So this means that after all of this, we still get back Ke plus Pe as we know it, right? As we know it. And I think it would be a fun exercise if you at home prove that this choice of P and Q are in involution with each other. I think it'd be a fun exercise. I, however, am going to be moving on. Actually, I have a little bit of board space here, so I was really concerned about board space. So, because I have very few sheets of paper left here. So actually, why not just prove it right here? There's not a lot of involution stuff to prove here because we don't have two variables, but I guess we could prove this. So remember that the Poisson bracket is equal to partial f partial u partial g partial p minus partial f partial p partial g partial q. Is that a lot of derivatives? That's a lot of derivatives in my opinion. Also just the notation, right? So we can actually pattern match this. Now, let's see. We actually didn't need to derive a Hamiltonian for this, but it felt like a nice segue. So you're getting this, I guess. I see one big glaring issue here. Or no, I don't see one big glaring issue here. Yeah, I do actually see one big glaring issue here. P doesn't depend on Q. It's not supposed to depend on Q, and it's never going to depend on Q because we chose it in a way that it doesn't depend on Q. It depends on the derivative of Q, but it doesn't depend on Q. Which means that this term, right, because F here is equal to P, and G here is equal to H, right? I'm only showing this one. You can show that. You can show that one yourself. It's easy enough. Let's see. P or F doesn't depend on Q, so this immediately goes to 0. Or, excuse me, that's supposed to go to 0, not theta. And that means this also goes to 0 because anything multiplied by 0 is itself. And this term becomes partial P over partial P partial P. That goes to 1. And this, what does this go to? Well, this goes to P dot is equal to -1 times partial H. Partial Q, what do you have it? What do you have? This is the same equation that I wrote on the very first slide that I'm not going to flip back to because the paper literally gets caught on the ceiling. I'm not even kidding. Yeah, so we didn't really need to derive a Hamiltonian for that, but we did, in fact, prove that this is correct. Amazing. Now, I've done far too many takes of this video already, so I'm kind of working with limited board space here, which means I was originally going to do another example here, but we might have to go directly into the KdV, the Korteweg-de Vries equation. It's an equation, chat. Oh my gosh. I should... People. It's an equation, y'all. The Korteweg-de Vries equation helps us model shallow water waves. And the cool thing about this equation is that it is integrable. Now, who knows what integrable means? Yeah, right there. I'm pointing at a water bottle. Integrable means that we can solve it exactly without having to resort to numerical approximations and perturbation theory and all that good stuff. Now, the Korteweg, I'm going to pronounce it Korteweg for the duration of this lecture because I don't know. Says that u tt is equal to I was originally going to do another example here, but I also don't have to tell y'all that this is the Korteweg-de Vries equation yet. So treat this as just another example, okay? Let's have ut plus 6. What the hell's going on in my computer? Hold on, I am having technical difficulties here. Well, Zoom is still working, so I don't have to worry about it. Ux plus ux is equal to 0. Okay? Now, glaring problem. This is not a total time derivative. This is a partial derivative, right? A subscript here indicates partial. Partial t. So what do we do? Well, we multiply, we do this nice thing with power. If you remember from high school, power is equal to force times velocity. And energy is equal to the integral of power dt. Another thing that we have to take into account here is that this is a field equation. All right, so it means it's continuous. Now, how does this affect these two formulas? Well, it affects them in a pretty big way. E field equal to, we have to add another integral, unfortunately. But it's okay because integrals are fun. We have to add an integral with respect to x. Now, this may seem unintuitive because, like, where did that even come from, right? We have these two equations, and it just randomly popped up here. I have an explanation. The explanation being that we have to sum over the entire field, right? Because usually when we consider a system in physics, right, in like introductory physics courses, we consider a ball, or I don't know, honestly. Yeah, we usually just consider balls. Yeah, just balls. I don't even have them. This is unscripted. I genuinely cannot think of another example other than balls. But this is a bit different. This is fields. And in fields, everything matters. So, like, it's not necessarily that it's, like, non-local. It's more that we're just considering more than one ball, right? And the balls are scattered across the surface. And each of the balls matters. So we have to sum over each of the balls. It's just that the balls are continuous. Okay? So, what is F? F is equal to MA. I sincerely hope everyone understands that F is equal to MA. A is acceleration. It is the second derivative of position. And what we can get from here is what can we do here? Actually, I'm not quite sure. Because the example I had prepped already had UTT within the actual equation. But you know what? This is a field. What else is a field? Force is a field. Okay? You know, like in those superhero movies? Yeah, where like, I don't know, Superman makes a force field around himself to like not let the bad guys get to him. This is similar to that, except it's more physicsy. So let's just treat this as F, because both are a field, even if this is not a very canonical approach to energy. It makes sense mathematically, to me at least. So let's just field, not feed. I don't know what feed is. And by virtue of Leibniz, we are allowed to move this integral back there. See? You'd see for V, right? A little bit big. See? And then dt dx. Now, this is probably an integral. That's probably an integral. This is an integral that can be evaluated right off the bat, right? We don't need any fancy stuff for it. No, I don't exactly have the solution memorized, and frankly, this integral scares me because there's this whole component, which I'm pretty sure also depends on t. But what I do know is the final Hamiltonian. Are you alive? Hold on. I think it's fine now. I think it's fine now. Okay, so I don't know how to evaluate this like off the top of my head, but I do know the final Hamiltonian, and the final Hamiltonian, or the final energy field, E field, is equal to 1 over 2 u x squared minus u to the third dx. This is slightly a precarious position that we have gotten ourselves into, isn't it? We don't know what U is. We don't know what U is. That is what we are trying to find. So we can't exactly evaluate this integral. So like what do we do now? So it's an integral. Integrals are scalar. We don't want our Hamiltonian to be an integral, right? Right? I mean, who wants their Hamiltonian to be an integral? Well, I don't, but unfortunately, that's just the way that this problem works out. Right? We don't know U just yet. It's what we're trying to like find or analyze through Hamiltonian mechanics. But what we can do is just try to work with this, right? So we've arrived at this expression. It looks correct. I mean, it looks pretty mathy to me. I mean, it has U, it has X, it has 1/2. It doesn't have any T, so that's helpful. So yeah, it should work. The problem is it doesn't, right? With the Poisson bracket that we have already defined, we don't know how to work with this because this is what we call a functional. Poisson brackets, or the one that we defined above at least, it doesn't know how to work with functionals. We need variational calculus. Now, who here likes variational calculus? I certainly do. I genuinely do like variational calculus. And one of the things that exists in variational calculus is variational derivatives, right? So a spin on derivatives. Who doesn't like mu derivatives? Now, let me give myself some space here. It's still the same topic. I still want to reference back to this. The Poisson bracket for this specific system, for this specific Hamiltonian, is, and this is specifically designed for functionals. So this is actually going to work. F G is equal to the integral. And this Poisson bracket is itself going to be a functional. It's going to be the variational derivative of f with respect to u times partial x of the variational derivative of g with respect to x, and that integral is evaluated dx. I ran out of space on the board. Now, this Poisson bracket, it has a specific name. I'm pretty sure it's called the first Hamiltonian form, but I'm also not completely sure about that. So I'm going to be going with this. Actually, I'm gonna put a subscript of KdV there just to differentiate. So if there's no subscript, just assume that it's a canonical. That's a canonical thing. Now, what is the symbol that I have written that looks like the Kronecker delta, but is not the Kronecker delta because math people really like delta for some reason? Well, it is the variational derivative, and the variational derivative is defined to be f some test x, right? It's not the same x there. Some test x and some other variable y, right? Just to illustrate. Hold on. This is wrong. No. So it's minus some small delta, some small var x, that's how I like to read it, minus f is equal to, I don't trust myself to get this right, unfortunately. Hold on. I had it. I swear I had it. Yeah, I do have it. Okay. That is equal to the integral. Oh, yes, var f var x and whatever f originally integrates with respect to. That could be dx, that could be dy. We don't really know, and we don't really care, right? I don't know if I'm supposed to include the y here. I might not be supposed to include the y, but that's the gist of it, right? So f is originally a functional, which means that this integral comes from the functional itself. It's not something that the variational derivative introduces. So when we deal with variational derivatives, we're usually gonna have an integral sign out front because for it to like mesh together well, we kind of need it to be an integral. We kind of need everything to be a functional. If we're gonna have the Hamiltonian be a functional, we kind of need everything to be a functional. Now, let's get an example of this, right? I'm not gonna be working with the Hamiltonian quite yet. I'm just gonna write some f is equal to because that would give me just like any function that they can think of. Let's say x squared dx. Oh no, wait, no, u squared. Wait, now hold on. Let's be something more complicated than that. But it's fine. I think it's fine. Hold on. I don't know how well that example is gonna go. I feel like it's gonna be a little bit trivial. But that's okay. You know what? Trivial is better. Trivial is better for illustration purposes. So yes. Let's make this x, right? F is now you could evaluate this integral f, or you could take the variational derivative of f with respect to x, and how we do that, right, from the previous slide. F, I know what I'm doing wrong. This is supposed to be t, and x is some function which depends on t. Yeah, okay, yeah. X plus var x minus f of x. X is also a function. X is also a function. It just happens to depend on t. Right? It just happens to not be one of the variables that we're used to being functions, right? Let's plug this in, right? Integral squared dt minus integral of x squared dt. Now, the next thing about variational derivatives is they don't care about terms that are higher than this, right? They don't really care about terms that are higher, which means that when we expand this out, my math's that rusty. Come on, chat. Come on, y'all. X plus 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 var x squared. I was thinking about how to denote this properly without it seeming like I'm taking the second derivative, which I'm not doing. Minus x squared, right? I'm taking it right in. Now this cancels, and the variation derivative also doesn't care about this term because it's higher than. Let me show y'all. The variation derivative doesn't care about that term because it only cares about what's being multiplied by this, right? And this should not depend on var x. This should not depend on var x, and it does not depend on var x. Now, which means that this looks like 2x var x plus var x squared dt. And as you can see, this is the thing that we are multiplying by var x. And so hence this is our var x, var x. And what do you see here? What do you see here? Delig, I actually want you to look at this and look at the fact that this is 2x and the fact that the original integrand is x squared. What do you see? Well, I personally see that this is the normal derivative of this. So effectively, the variational derivative is just a way for us to get into the integral, right? For us to like pull the integrand out of the integral and take a derivative of that, basically. Now, in reality, this is taken as var x goes to 0. But I've already assumed that it's like small enough, right? And it really doesn't like affect things a lot. Now let's try to form equations of motion using the Poisson bracket that I've defined above, and using the definition that. Actually, I should clarify something. Even though, like, I should clarify what we're treating as P and what we are treating as Q and what we are treating as what, right? We don't exactly get as much of a choice in this kind of derivation as we did in the derivation where the original equation had a total derivative already, right? Like the first example with the nonlinear oscillator. But so here, if I remember correctly, we are treating U as Q. I'm just going to be using this symbol to mean set to. Write about it in the comments if you'd like. And phi, I probably shouldn't make it phi actually. Whatever. I'm gonna make it phi and clear up any ambiguities later. And phi is gonna be p. Phi number appears here, which is just yet another sign. If you were not convinced enough that we are completely in the woods, right? We're not out of the woods at all. That this is not in fact k plus p. This is scary, right? Right. So let's see. If I set to or notated out, I don't really know how you want to read this. This is just the notation that I use. It's probably bad. Right, so using the definition that for the Hamilton's equations that we used above, like the more general one, which is it's why I said that, like that is more general because of this thing that we have to use. Now, this example out of the way. I might write something else. I might write some other math thing here, maybe like the integrals that I might or might not take. Let's see. U dot is equal to, what is U dot equal to? I wonder what U dot could be possibly equal to. Well, U dot is equal to the Poisson bracket, or the KdV bracket, I guess you call it, of U and H KdV, just so we don't get confused. Now Poisson bracket time. I don't remember it off the top of my head, unfortunately. Now you can verify this yourself. I'm not gonna be doing that. But this is 1. Right? It's kind of an important property for derivatives to have. That a derivative of a function with respect to the same function has to be 1, and I forgot the integral sign out front. And times partial x of var h var x. Now, I'm like 90% sure this cancels. Like 90% sure this cancels. I'm pretty sure the Poisson bracket allows for this to cancel. Because, like, I don't know what I'd be doing if it didn't, honestly. Which means that U dot is simply equal to this expression here. Now, the neat thing about this expression here is that this doesn't like directly depend on x, right? Like this, I mean, U depends on x, and I'm pretty sure the variation derivative like carries it over into the functional itself. But this stuff doesn't depend on x. And I mean, we could take it, I guess. We always take it. But we would still end up with like an integral of something. We still end up with an integral. So you may be asking, what was the point of this whole exercise? We're no closer to a solution. And that is an amazing point. Honestly, that is an amazing point to raise. We're not here for a solution, right? I threw a bunch of mathematical concepts at you right now, but we're not here to solve the Korteweg-de-Vries equation. Yeah, that's right. I've been using the Korteweg-de-Vries equation this entire time instead of an example. Isn't that fun? Yeah, but we're not here genuinely to solve the Korteweg-de-Vries equation. I am here to show you what we can do with a partial differential equation, and what we can do so far is not a lot, but I think a lot of this whole point rests upon your understanding that we can do so much more with Hamiltonian under the framework of Hamiltonian mechanics than we would be able to. Not to say that we would be able to with just like normal differential equations, like the normal approach to solving differential equations, but it's still so important to be able to like think of a problem in a different way. Now, that whole sentimental rant out of the way, how do we know that this is integrable? Another rant is incoming here. Now, the original Korteweg-de-Vries equation is integrable. It is a prime example of an integrable, continuous partial differential equation. Continuous or infinite variable, it doesn't really matter what you want to call it. The thing is, we can't necessarily know that any procedure to convert a partial differential equation into a Hamiltonian preserves integrability. Because integrability of the equations of motion. The integrability of the equations of motion rest completely upon the form of the Poisson bracket. Now, if and only if the Poisson bracket stays the canonical Poisson bracket that I wrote out at the start, then yes, the integrability is going to be necessarily preserved because of the structure, right? Because of the structure of the Hamiltonian system, right? So if the system is originally integrable and it is canonical, it is canonically in a way that allows for the canonical Poisson, that the Hamiltonian formulation of that partial differential equation uses the canonical Poisson brackets, then yes, it is going to be preserved. I can't say always, but it's more likely than not, it is going to be preserved. Other things that can impact integrability are if some purely mathematical condition has to be imposed on the Hamiltonian for it to work, right? For some conditions of a Hamiltonian system to be applied, or simply for, I guess, not necessarily convenience, but for it to be like manageable, right? For this whole derivation to be manageable. These things can include discretization, choosing a specific gauge, or having to apply a transformation of coordinates. I'm not completely sure about the latter, but I think because of course you can like choose how to transform your coordinates. But in general, whether or not integrability of a PDE is preserved in turning it into a Hamiltonian, in formulating it into Hamiltonian mechanics, is that involution is preserved. Or not necessarily that both that involution is preserved and that something called a lax pair exists. Now, what a lax pair is it is a pair of operator variable such that under the Poisson bracket, which is chosen for the system, which is chosen for the system because I don't think it's like particularly canonical. It's just chosen. Such that when the variable is acted on by the operator in a way but through the Poisson brackets, we get back the total time derivative of the variable. A lot of words I'll say it right now. That was a lot of words. All it's saying is that there exists some, that's the wrong symbol. There exists some QH. I don't know if I should denote it like this, but yeah, Hamiltonian is an operator. Yeah, why not? Such that with the existing definition of with some PD, Poisson brackets, right? With some Poisson brackets, Q dot is equal to QH non-canonical. So this is a lax pair, right? Q and H is a lax pair. Do you notice any similarities between this thing right here and everything we just talked about? I sure do. I sure do. Now, specifically, I noticed that this looks an awful lot like one of the like the Hamilton's equation for Q. This is more or less notational coincidence, but it is not necessarily notational coincidence, because this kind of thing is important for the actual equation of motion to be integrable, right? Because this is basically the thing that we're gonna be integrating, right? For integrable, right? If it's integrable, this is gonna be the thing that we're gonna be integrating. So the existence of a lax pair like this implies that this, right, that the equations of motion are integrable. Most of the time, this is going to be the thing that we're integrating if it does end up being integrable. All right, so if integrability is preserved. If the system is originally non-integrable, Hamiltonian mechanics can't help you make it integrable. However, you may then be asking, integrable equations, integral PDEs are like so rare. Like, most of the stuff that you come up with in your head, most of the PDEs that you come up with in your head, they're not going to be integrable. So then, what is the point of this exercise? I keep coming back to this question. What is the point of this whole exercise if we're not going to be integrating anything, if we're not actually going to be solving, if the Hamiltonian isn't going to be some magical tool to get us the answer to the original partial differential equation. Well, what can I say? I can show you. Yeah, I'm not fully familiar with what I'm about to show you, which is why I'm going to pause the recording and the reason we did this whole exercise, even if it seems pointless, even if it seems like truly it didn't help us solve the original problem at all, which honestly, it didn't. I have not solved the Korteweg-de Vries equation within this lecture. However, what I have done is given you and given myself in preparing for this lecture the tools to convert something which to me is scary a partial differential equation into a format that is manageable, even if it is under a different formulation. We are using different derivatives. We are literally using different derivatives. We are using variational derivatives. We are using a different Poisson bracket. We are using a different form for the Hamiltonian. K plus P, that's long gone. It's long thrown out the window. The birds have already eaten all of it. But it is still Hamiltonian. It is still Hamiltonian, so we are still allowed to do things to it that are Hamiltonian. Now, the solutions to the Korteweg Rice equations are waves, obviously. It describes shallow water waves. The equation describes shallow water waves. So its solutions will look graphically something like this. This is called a solution. And this is a one solution solution, right? Assuming that this just pans out in all directions. I haven't drawn it very well, but assuming that this just like pans out asymptotically to infinity, this is the one solution to the KdV. Or like it's traveling like maybe in that direction, maybe this direction. Its speed can vary from solution to solution. There are also n solution equations, as n solution solutions, which can be things like this, and they can go in opposite directions, right? But they have to like pan out at infinity, right? In general, they have to pan out at infinity. I would like to talk briefly about these solutions and about why they matter. Right? So if you are at all familiar with, let's say, some kind of wave dynamics, right, you would find this inherently interesting. However, another thing that we can do to these waves is, or that we can do to the KdV, to the KdV equation, is impose a periodic boundary condition, right? What a periodic boundary condition is given some function u of x and t, let's say, a periodic boundary condition is a boundary condition that ensures that u of x of t is equal to u of x plus L C, and both are equal to 0. Which means effectively our solution space starts wrapping around itself, right? Because everything confined to x plus L can be effectively taken from the interval x plus L and then put on the next interval, and then put on the next interval, and then put on the next interval, all the way out to infinity, right? And this kind of boundary condition significantly doesn't necessarily limit our solution space, but it changes our solution space. So these waves right here are called solutions, right? As I've already said. But when we impose this kind of boundary condition, the solutions stop being solution and start being noidal waves. I assume the C is silent. I'm not sure if the C is silent, but these become noidal waves, and they go something like this. Isn't that pretty? I think that's very pretty. And of course, this is 0, this is L, this is 2L, this is 3L, and this is 4L. You get the gist, right? And nodal waves actually appear in a lot of places. You would be surprised. Honestly, I've only started talking about this to give myself an excuse to talk about the Fermi-Costa-Ulam single theorem theory, because I think it's funny that a theorem or a theory has pasta in its name. I think that's funny. So I'm just discussing the solution, but really I'm just discussing the solution space. So solutions are just something you would see. I don't know, if you pluck a string, I guess, right? Or if you like move a rope up and down, I guess. I don't know if that's like a perfect way to model it. But yeah, it's something you could see if you flick a rope up and down, right? It's just like a wave packet. It's just like this thing that has a height and an equation, right? And nodal waves are just a collection of solutions which go like this. Now, the nice thing about periodic boundary conditions is that they allow us to cancel out a lot of things, right? Because it may not be fully evident with the KdV equation, but it is evident in equations that are not naturally periodic, right? In that case, in the math of it, you will be able to cancel some terms, and that can be quite helpful. The way that these terms are canceled is when you are evaluating the integral. I can show the slide. I can show the slide. When you're evaluating this integral, for example, right? You're not evaluating it from negative infinity to infinity, which is what we've been doing. We're evaluating from negative infinity to infinity with the implicit understanding that u goes to 0 at infinity and negative infinity. So like it kind of like pans out, right? So no matter how far it travels, it's still gonna pan out in finite time, right? But what periodic boundary conditions do is they change these bounds to 0, L, right? L is the period, right? From this slide right here, right? L is the period. And when we do this kind of thing, and when we do this kind of thing, it also changes the bounds of the t. No, it doesn't change the bounds of the t. What am I saying? It can be helpful when evaluating this kind of integral because things start canceling out, right? We may not be able to completely evaluate this integral because we still don't know the form of u, but we are able to maybe cancel out some terms which end up being necessitated to be the same due to the periodic boundary condition. Due to this. So for example, if a periodic boundary condition is imposed on this thing, and if I disregard this thing here, this would go to 0 if I disregard this thing here. Actually, I'm pretty sure this would go to 0 even if I don't disregard this and this, because yeah, it would still go to 0 because this is required to be 0 at both 0 and L, right? So I think that is Pretty neat, pretty helpful. Another thing that periodic boundary conditions can help with is action angle variable theory. I have done a video on action angle variable theory. I'm not fully sure if I went over this fact that in like a lot of detail. But the way that you choose the bounds for integrating your action variable j from some a to some b of PDQ, right? So this is the action variable. You can leave now. If you don't understand what I'm talking about, you can leave. The meat of the lecture is done. Right? Depending on how you choose these bounds, and depending on if you determine the motion to be oscillatory or rotational, this can evaluate to be very different, and it can also evaluate to have a different physical meaning, right? A different physical interpretation for what we have found. Nice thing about periodic boundary conditions is they basically set these bounds for us. There's no extra work involved. So, yes. I have not proofread what I'm about to do here, so there could be mistakes. P. But I'm just assuming that the Hamiltonian from above already has periodic boundary condition imposed on it. That's probably not the case. Okay, P. The original H doesn't depend on P, does it? The original H doesn't depend on P, so I guess we can't exactly apply action angle variables here without a more specific choice of our variables that may also not be in involution with each other, that may also not satisfy the lax pair thing, or not satisfy the lax pair thing, but more like not that they're not the things that are specifically in the lax pair. I also wanted to show y'all the actual lax pair because this is not because I'm pretty sure this is not it. And I do have it in my notes. I think I've been wrong about what I said about the lax pair thing, but I'm gonna write out the lax pair anyway. What I have is I can just stop dropping this thing. Right, and suitable choice of L and P here. And I'm pretty sure you can verify this yourself, or just look it up, honestly, because I'm not fully versed in what lax pairs not understanding in what they are, but what they do in this case. Negative partial squared x plus u of x, and this is canon. This is the canonical one. I'm pretty sure. P is equal to 3. Nope, it is not equal to 3. It is equal to negative 4 third x plus 3 plus 3 partial u partial squared. No, just partial x. Wait, no, this can't be the case. Plus partial x. Oh, this isn't a Poisson bracket. This isn't a Poisson bracket. This is a different kind of bracket. This is a different kind of bracket, and I might have to talk about this more in depth in a future lecture. Actually, I think I will, because this is interesting, and I feel like it would complete the lecture more. But what this is that it basically acts upon that operator, right? So this is the Newville. And I was wrong about my previous definition of the Lax bracket because I thought it was with the Poisson bracket itself, because I thought it like had something to do with the Poisson bracket itself. So I kind of like merged those two ideas. Disregard what I said about the Lax bracket previously, and look this up instead. And I might do a lecture on this in the future, because I do think it is quite important, and I think integrability in general is a very interesting subject to talk about. So, on that note, I hope this was interesting. I hope this was insightful in one way or another. I hope you have enjoyed this lecture and this overview, I guess. Yeah, it's a pretty bird's eye level overview of the subject, but I think it's important to have bird's eye overviews of more advanced topics, simply because it's important to also have like nitty gritty, like low level approaches. But I think to just get your feet wet and to not be, I guess, like scared or intimidated by all of this, I think it is important to have things like this. So yes, I'm totally just justifying this for myself. But yes, thank you for listening, for reading, for coming. Thank you. I'm thanking the 2 water bottles on the other side of the boardroom here. But yes, thank you for watching. I hope I will see you soon, and I will see you soon. Yes.